Very good morning all of you for these lectures on river equilibriums, in which we will discuss about Lacy's equations, river meandering and the regime relationship, which is quite important for us to know it. How does a river behave under changing discharge or the sediment load conditions? That is a bigger questions, and that is what we try to address through the regime equations concept. Now, if you look at the next part what we are talking about, which more or less we are following it Julian book, as well as partly we are following it the experience of Indian Railways engineers on how to protect the river banks and river training works for the railway bridges. So, both the things we are combining it to discuss about what is the regime concept and how we can use the regime concept for the efficient river training works or the bridge protections, the extreme flood protections of the bridge. So, if you look it that way, if I look at the last slides, which is again I am repeating it to have the basic knowledge is that how the things are moves it, that one is the river survey, which we can do from the field level of studies. You can have the drone level of studies nowadays, or today's we can also use high resolutions satellite imagery to understand what is the river platforms and how the river meandering geometries. Those are things we can understand of the river and its river corridor associations by conducting a thorough survey either at the field scale or using the satellite platforms. We can do it. What we target it? The flow variables, sediment variables and the meandering characteristics. And once you get these all these variable data, the flow, sediment and meanderings, then you try to establish the relationship between. That is the reasons you use the data mining tools, okay. Very older concepts like correlations techniques, now they have 3D visualizations technique, and there are a lot of algorithms in the last 2 decades has been developed for data mining from a large data sets. There are a lot of examples and also the evaluations we can have. So, the basically is what we have these are the equations, the empirical relationship what today we will discuss about, the Lacy's concept, and he also as discussed earlier the analytical studies focusing on variations problems, large scale eddy concept and entropy concept. We try to establish it this relationship with the physics. That is what we try to do, analytical solutions of the river flow with certain assumptions to establish this variation concept, the large eddy concept with the empirical equations, the entropy concept with the empirical equations. So, that is the advanced level going on, and this is the flow charts what is there to know it, how we can find the regime equations. Now, let me I go for the next ones is very interesting is that, and if you look at the graphical length relationships, okay, which talk about is a balancing. The river does a balancings between the stream powers, that is what is the energy dissipations, and the carrying of the bed loads. These are balancing effect is there in a equilibrium river reach. So, if you look at that, it is a very interesting balance is there, and if you try to look at one side is a discharge and the stream slope or the river slope, okay. That is discharge and into the stream slopes, it is indicating for us the stream power per unit weight. What is the stream power is there or the energy expenditures is there. That is what is balance with bed loads and the sediment size. Okay. So, if there is a unbalance, either the bank will go for erosions level or the aggradations or depositions levels. If both are balanced, there is a equilibrium stage. If there is a the higher value of Q and S, the stream slope and this discharge, the product of discharge and the stream flow, which is a stream powers per unit weight. That is what is indicating is that if it is this is the higher value, that has to balance by the sediment size or the increasing the bed load. That is what will have the bank erosions process will be significantly go more, or if you have a this case you have a aggradations. That is what is my suggestion is that you just sketch these diagrams, try to understand it, how does a river behaves if we change the sediment load, change the discharge or change the stream slope, like we do the sand mining, we change the bed slope of the river systems. We have been doing the sand mining, gravel mining of the river bed. So, we are modifying the stream slope. As we are modifying the stream slope, what is going to happen, whether it will be aggradations or degradations, or you do the sand mining. So, just try to understanding that if I doing the sand mining, which is today is a very critical issue in our countries. If you look at that, so you are increasing stream slope or the decreasing the stream slope. So, we are modifying the stream slope. We are changing this D50 value. Mostly we are doing the positives. We are armoring the things. So, we have if you have modifying because of the sand mining the stream slope or modifying this sediment size. So, definitely there will be a change in the bed load, also there will be a change, and because of that change there will be a change in the morphology. So, that is what we have to try to understand it. When you have a equilibrium river, in that position there is a balance between the stream power per unit weight with the product of the sediment load and the sediment size. So, if it is that the balancing is not there, then either we can have a bank erosions or we can have a aggradations. That means the equilibrium concept will go out, it will start either the erosions or aggradations, and the river may be morphologically active will be there. So, if you look at that, it is very equilibrium concept with the hydraulic conditions of the left side, which is talk about the stream powers or energy dissipations per unit weight, and the sediment constants on the right side. We have a QS, and that is what QS stands for the sediment loads, ds is the particle size as we discussed earlier. So, if you understand these figures, and I try to tell you that please remember this balance which talk about how we modify a equilibrium rivers. If you modify by conducting a sand mining, or you in the cases you can increase the discharge or decrease the discharge, or so how does it affects to the sediment size or the load. If I look at these equations, this equation has come with a very simplifications of same regime equations with a some assumptions, like if I look at the bed transport relationship, which is a bed load per unit width is a functions of ds and the silt parameters. So, silt parameter is a ratio between the bed shear stress and the weight of the sediment particles. So, that is the bed shear stress part is coming here in within the silt parameters. Then if you want to compute is total bed loads, which will be the unit bed load per unit width and the multiplications of width of the river, and that width of the river we can approximate with the previous regime equations, where is QB stands for unit bed load discharge, ds is a grain diameters in meters, QB is a bed load discharge by volume. Okay. So, now if I substitute these equations, that is what is I am just substituting the W value, okay, which is a relationship with Q dx and the S value, and if I just rearrange it, I am getting the same format what is there in the length concept, if you look at that. Okay. So, if you look at that, it is just like a length concept, where is q to the power 1.11, s to the power 1.44, and these multiplications are there. So, what it indicates is that if I use the regime equations, also I can derive the possible form of this length formulas, which establishing a equilibrium between the stream powers or the energy dissipation per unit weight with the sediment load, the river sediment load in terms of the bed loads what is here. So, if you look at that way, that is a downstream hydraulic relationship, it is not for the defining the station process sediment rating curves. Okay. You try to understand that it is not for the sediment rating curves. So, if I increase the dominant discharge, the Q plus, okay, expected there is a climate change and we will have the more oftenly this dominant discharge is going to increase it. If that is the conditions, if I look at equations, what we are going to increase to balancing that, width can increase it, because that is what is here. The H can increase it, that is there, because as this Q is increasing it, we have to increase to make a balancing effect it that. So, either the bank fold width will be increased, the depth will be increased, the slope has to decrease, that is what is here, to or there will be decrease in the silt parameters, but those are very long term process to change the silt parameters like a D50 values. The bed material of the rivers will not change so drastically within the few years, within a decades. It is a very long term process happen for the alluvial depositions. If you look at that way, if I summarize that, if there is a climate change or deforestations, okay, deforestations, expecting this dominant discharge is in a positive trend. Okay. If that is the conditions, from these Lacy's equations, we can easily find out that river will be response at width to be increased, okay, or the depth to be increased, slope should reduce. Okay. So, that is what I am going to try to understand it. The regime equations we can put it to know it how river is going to respond it if there is a dominant discharge is in a positive trend. That means, because of the climate change, because of deforestations, the dominant discharge is increasing it. If that is the conditions, the river width, the flow depth is supposed to increase it, whereas slope can also decrease it to have this, because other part like a D50 values, the silt parameter, shear stress, those are not going to change within a few years. It takes longer times. It is not a decadal levels, it is a beyond the decadal levels. So, changing of the D50 is that. So, if you can understand it, if there is a increasing of the dominant discharge, that is what is going to affect width and the flow depth, and there will be a negative decreasing trend would be there in the slope, the river slope. Now, if you look at next questions, if I look at that the dominant sediment discharge is in positive trend. Okay. So, if you have look at this Q B into D is equal to Q and S, this is the discharge, this is the sediment discharge, this is a D values and S is a slope. If I am making this is a positive value, so to making the balance, the slope has to go increase, Okay. So, that means the shallow slope can go for default slope, okay, can have an increase in the slope to balancing that, or you can have a the velocity can increase it to increasing this part, okay, or you can have a significant increase of the shield stress values. Okay. That is what is the QB increase means, it is they are in part of shear stress, slightly decrease in channel width and the flow depth. Okay. That can be happening, but the grain size distribution comparatively less significant except in decrease in the shield parameters. So, you try to understand how the river is going to affect it if the dominant sediment discharge increases. If you look at this increasing the length concept, is a relationship between the dominant sediment discharge with the D values and Q and S, the discharge and the slope of the river. As this Q is a increasing trend, definitely to balance it, either Q to be increased, the velocity is to be increasing trend, or the slope to be increasing trend, or you can find out will be a positive trend increasing on that part, okay, and there may increasing in grain size are comparatively less significant, okay, except in the decrease in the shield parameters. So, if you can look at this diagram, you can try to understand what is happening it. When you have a river systems, if there is a change of the flow, change of the sediment discharge, both will be affect in terms of changing this, the flow geometry in terms of width, depth and the slope and the shield parameters. If our sediment is increasing, there is increasing in all these factors, the slope, the velocities as well as the tau stars. Okay. So, that way you can try it the conditions where in which conditions we are going to have the dominant sediment discharge will be in increasing trend, or same way you can anticipate it if there is a Q will be the negative, okay, as you have the reservoirs you can regulate it the dominant discharges, okay, or QB the sediment discharge is a negative trend, that way you can also interpret it which you are going to increase, which are going to decreases. So, the Lenz equations talks about us how we can anticipate it which are the going to increasing trend of the flow parameters, flow variables or the channel characteristics, that we should try to understand it. Now, if you look at very basic things, the river bed degradations like the for examples you have a river initial level like this, the width does not change it, but the depth is increasing, okay, h naught to h 1. Okay. So, when you have a lowering the bed elevations due to the erosion process, okay. If that is the river bed shifting, the bed material is fine, then channel insertion will happen. Is material is sufficiently coarse, then river bed armoring is going to happen. It for incised channel, what it happened is that outgoing is exceeds than incoming sediment loads. That is try to understand it. Why it happens it? The incoming sediment loads is a lesser, the outgoing sediment load is more, because it is a deepening the channels, okay. And the stream slope in increasing the downstream directions, which is just a reverse, okay. For a generally you go to downstream reverse, stream flow, stream slope should decrease it, but if it is a inside channels, you will have a increasing trend. The scouring and degradations of the river bed, that is what you can show it. The result in channel increases the middle slope, narrow and deep channel, and there will be the banks will be the unstables. So, we can have a reduce the width, okay, before and afters, and the shape can come like this. So, you just look at how this river bed degradations happens it. Same way you can graphically you can just to understand it, is a very easy things to understand it. that you can have a calving process, you can have an undercutting process, the high flow, low flow is there, and this is the cutting part is there, galling process, and you have a incising process, entrenching process. You can have a like this, okay, though deepening the channels, or you can have a the armoring processes are happening it. Okay. So, these are just looking the figures, you can understand it how the process are happening it, and we are not going more details, but let us have the knowledge that as the flow variables are there and different type of different river degradations can happen. Now, if you look at river planforms, okay, if I look at nowadays is too easy from Google Earth imagery, we can see the satellite data and we can see what is happening to river planforms. Okay, that is very easy to look at. Look at these rivers which are regular river meanders. Okay, it's very easy. It's very interesting river meanders which is there in part of the Narmada rivers. But here this the wavelength or the amplitudes of the meanders are the different. If you can look at these two rivers, okay, which have this. But if you look at the sharp river meanders can go for like this shape, it can go like this shape and come back like this. So, if you look at this way, river meandering shapes can have a like this shape. So, it is a quite interesting. Or if you look at the river which is in Assam's Dangori, so if you look at the shapes, okay, it's too complex. Okay, regular intense meanders are there. The meanders which are clearly visible, and there are the complex river meanders like this. If you look at these figures, okay, it's making I am sketching it to understand the nature's art form. Okay, so sometimes it's quite regular river meanders, and we can have a sometime very complex river meanders. We can see it from the river. It talks about the basic characteristics of the flow variable, the bed materials, the bank materials, all it talks about. We should try to understand why it is river is a very regular meanders to the regular with the intense meanders or the complex rivers. But let us try to understand it. Simple river meanders, when you talk about that, how things happens it. If you talk about any rivers, okay, river can have a shape like this. It's very simple shape, it can follow it. Okay. River is controlled by these two narrowest reach, okay, two narrowest reach which we call the nodal. Okay. So, you can see that in a river many locations there is a nodal locations, the constraint reach river cannot have any degree of the freedoms. Okay. That is the confined it. So, the mostly what it happens to the rivers, that when you have the sediment discharge, okay, the energy dissipations all are changing it. It's all are not a constant for the river systems. Sediment discharge, energy dissipations all are changing it. So, river what it does it to respond to this, it's try to make it as different reactions at the different times. Okay. Like for example, it can behave like this, again it can follow like this. Okay. It can happen that, because at the nodal reach it is a constant that, or it can follow this way. Okay. So, river with a two constraint locations, river can have a different response. To know it, to make these very complex rivers, we always look at a simple way with a circular arcs. We can you define it, the river behaviors between two constraint locations, how does it behave it with this may be different years, how the rivers are behaving it, we try to make it different circles. Okay. If you look at that case, this is the case we are looking at here. This is the case we are looking for here. This is the case we are looking for this case. This is the case is a very symmetric case we are looking from this, or this is the case we are looking for the river to go like this, or we are looking to river to go like this. Okay. Just you look at the shapes, okay. That is it is a nature's art, okay. That is we should try to understand it, okay. And with a circular arcs we can define these meanders, okay, and that is indicated for us the science to know it, what the ratio between d by r. D is a vertical distance between center of successive circle, and r is a radius of circle, L r the length along the river, the LV stands for length along the valley. So, if you look at that, this way river can have this different response, and we should try to understand it, why does it happen and how river is going to respond in different way. These are really interesting work, and we should look at more advanced levels that how the river is responding between two nodal locations with the different conditions. You can see it in next, I will slow it. Now, if you look at, if I go to the next level, very simplified way, if I make a river meanderings, okay, with starting from with a one inflection point to another inflection points, okay, this is my meanders, okay. It is not exactly circular arc, okay. The theta m which is maximum angle here, and the theta angle is changes it, okay. This is the two crossings, and I define this is a meander length, okay. This is the meander length, this is what meander belt, meander width. So, you can see that center to center point of the channels we can define as a meander width, we can define as a meander belt with a side to side. So, if you look at this way, if we can define a meander in river, and W stands for the width, and R is a radius which is minimum here, or at this crossing point will be the R will be infinity, and you have the radius. If I define it, there are many debate about this meandering process. There is many say that this is a secondary flow which is playing the major roles. Perturbations theory, there is a stream hypothesis like minimum stream powers and minimum variance concept. So, but if you look at that way, we try to understand is if that meandering length, meandering width, radius of curvature and channel width and channel length, and if I consider this theta is a cos functions along this length, okay. This is the x distance along this river, okay. So, cos distance along this rivers, if you talk it that, and if theta is varying as a cos function of x, x is along these ones, if you look at this, that case you have a theta is a functions, you can compute the meander length, the length along these curves, that is what you can get it in these functions. If you compute the sinuosity, okay, it is defined by the length, river length divide by this the meander length, okay. The river length divide by this meander length, if I put it that. So, I will get it the in terms of theta m functions. So, this sinuosity is playing the major roles. If you try to look at the earlier figure, the satellite imagery, we can compute the sinuosity which is the ratio with the length by this meander lengths, okay. By this the meander length we will get it which is a functions of the theta m. So, we can also get this radius of curvatures which is just a geometrical formulas, we can establish it and we can know it what will be the radius of curvatures. And if I look at minimum radius of curvatures, I can get it meandering width, also can get it a functions like this. And if I plot it, that is what is, let me looking the properties of meandering rivers and plot it with sinuosity, a non-dimensional forms with Mandrel length by this Rm, there is a ratio, non-dimensional ratio. If I put it, what I am getting it that there are 3 zones, clear cut zones. Okay. Here we are putting the theta m. Okay. So, when theta m in the degree scales is more than 110, then there is a neck cutoff will happen it. Okay. Below 30 degrees you can call it sinuous reverse, then it is called meandering reverse. And if you try to plot it, how this sinusity increases, okay, how is this meandering width by length is increases, okay, how this minimum radius of curvature is there. So, that is way we can have a characteristics of the reverse meanders in terms 3 classifications of sinus, meanderings and neck cutoff. How do they are behaving of sinusity? That means, as the theta m is increasing, your sinusity is going to increasing, okay. Meandering width is going to increasing, the ratio between W m this meander length will be increasing trends, and you will have the minimum radius curvatures will follow this. So, these indicating us what is the characteristics happens when you have a minimum radius of curvature for given meanders is coming out to be 75 degrees. Okay, that is what if you look at that. Okay. That is what you can look at that, and meandering width increase rapidly as theta m exceeds 90 degree, it reaches the value 3.25 at the cutoff. So, okay. So, what you are doing that it is the value, if you look at these ones, it reaches around 3.25. Okay. After that this process is cut off it. Okay. So, reaches the value theta m exceeds the 90 degree, the increasing strains, meander width is increases rapidly this zone, okay, and reaches the value 3.2, meanders cutoff happens, which is a theta will be the 125 degrees. So, the cutoff will happen it here 125 degree. So, these are the basic characteristics. If you have a knowledge about that, looking the meandering characteristics, we can identify at what conditions it is going to have the meander cutoff. Now, if I look it, there is a lateral migrations, river migrations. Okay, river also migrate in the lateral directions. If I quantify the energy gradient along the valley, here I am talking about energy gradient along the valley, which is the ratio between energy losses over a meanders having the wavelength and the friction slope as S naught. So, we can compute what will be the energy losses in the valley directions and the energy losses, which is in terms of your the basic the sinusity functions. Okay. And if you try to look it with theta m and the reverse sinusity, try to understand these figures, okay, which is very interesting. Figures are indicating it that if I put for a river meanders, you have a theta m value which is in a radians, and I also have a ratio between radius curvatures and the width. I have the sinusity values, the functional relationship of transversal shear stress will follow like this, longitudinal shear stress will follow like this. Okay. Just you look it. This is a relative shear stress is showing it for the transversal shear stress and the longitudinal. So, it is quite interestingly at 1.34 sinusity, the theta m values and RMW values, at that locations you have a transversal shear stress is much higher. Okay. After that there will be decreasing trend, and before that. So, this is the sediment transport. If you look at, this is the low part and this is the high part, is indicating how the sediment transport is happening it. So, let me have a put it the sinuosity varies with a theta m. The ratio of the silt parameter for meandering channels is a function of the theta m. If when theta m is above 90 degrees, silt parameters of a meandering channel is less than half of the straight channels. So, you can try to interpret this the graphs giving a relationship between theta m, the sinuosity with a relative shear stress. That understanding can give us how does happens the lateral river migrations. If we look at these figures of the two figures, first let us see we discuss about the Kameng rivers, okay, which have a 2002 1988, okay, this is a span of 14 years. If you look at that, these are nodal points where the rivers are something like this, okay, and further it changes the rivers, the figures are this. So, there is a lateral migrations of the rivers, okay. So, if you look at that, there are the lateral migrations of a river, or I can say it, rivers behave like the pendulums, okay. If this is the nodal locations, okay, this is the locations of the nodal locations, the river is behave like a pendulums. So, it's go like this, okay, just swing it, okay. What is the time periods of this swinging is always a big question mark. What is the time periods? Does it take 4 years? Does it take 12 years? Does the time periods access the 50 years? We do not know it. That's the concept we should look at, and if you just try to understand it, it works like a pendulums, and it has a time periods. And what is the time periods of these lateral migrations? That's we do not have a much precise answer for that. But if you look at that river course is 100 years old, 70 years old, 50 years, 30 years existing course of river Ganga at the Patna. There are the two nodal locations. That is the nodal locations. This is also a nodal locations. The two is confined. The nodal locations are there. Two confined nodal locations are there. The rivers are weaving. It's a very good pictures which provided by this Indian Railways Institute of Civil Engineers. You can interestingly look at what is happening these rivers. How this rail color is existing channels. Okay, the existing channels are behaving like this. Okay, just if you look at the 70 years back, it was here. Okay, and these channels again bifurcating it here. So, the bifurcations are happening here, and these are oscillating behavior. As I said it, in this case it is oscillating between the 2 points. If I look at that, I have the spring, it can oscillate it like this. Okay, it can have a oscillations like this. Okay, just you try to understand it. If there is a 2 points and the string can oscillate it in the lateral directions, and it has a time periods. Here you can see it river 50 years back, that the conditions, and the 100 years back and 72 years back it was here. So, it's just move it from north to south. Okay, the river flows from west to east, as you know it, west to east, and the northern bank and southern banks. So, if you look at this river, very interesting figures are there. 70 to 100 years back, the river used the south bank. Now, it has shifted to the in the northern bank. We do not know how long it will be there. Maybe another 50 years it will be returned back to the south bank, and how the things are happening here. So, these time periods of oscillations, lateral directions, all are big questions mark for us, and we should try to understand our river systems, how does they behave it at as a lateral river migrations. There are a lot of data nowadays available, the old data and the new data set what we are capturing it. We should try to look at how does have these time periods as indicating the two rivers. One is the Kameng rivers, another is Ganga river at the Patna locations. Now, if you look at coming to a regional relationship, okay, which is very interesting to know it, that way back 1863 Ferguson's established that the ML is a meandering length, okay. ML stands for the meandering length, is a 6 times of the width, okay, which is necessary to know it to give enough space to the rivers. That means, if a width river is 1 kilometers, the meandering length will be the 6 times of that, okay. It will be the 6 times of that. That means, it will be 6 kilometers, okay. That is what is ML is that. MB is the width of meander belt. So, we are talking about this width of meander belt, which is in 1902 very simplified. I can say that the meander belt, if I approximate it, is 18 times of W. Is this there a spatial frequency, and it also maintains the rivers 6 and 18. Just try to understand it. That means, if width river, if I know it, its space width of the river is a half kilometers, then 9 kilometer is a meandering belt width. If a river width is a 2 kilometers, then is a 36 kilometer is a meandering belt width. So, we should try to understand it, not look these equations only, which is developed way back in 1863, 1902, okay, it is almost 118 years previously. There was no satellite imagery and all. So, if you look at that way, it talk about a concept that there is a spatial scale of meanderings, that meandering length will be 6 times of width, meandering belt width will be the 18 times, which easily we can remember it, okay, if we are not looking at precisely. So, if you look at that English, which is considered the American rivers, and some of the rivers from Odisha state of India, which is such that this ML and MB can have a ratio of MB by ML. I can say that it is a close ratio of 0.35, or we can approximate is a 0.33. That is the same concept. That means, the meandering length and the meandering belt will be the 3 times. It is 3 times. That is what is we should try to understand it. It is a 3 times. So, if you look at that is what is Jefferson's data, and with this. So, if you look at the length and width with the resistance, the same way if you look at that Leopold at 1964, considering the large rivers, again it has come with in terms of width is a 11 times, and MB is a 3 times. Okay. Okay. So, here in case of the large rivers, the ML is coming about to 11 times and the 3 times of the width. Okay. And if you can look it is closer to that. Same way, if you look at that from experiment model data, can have a ML MB relationship, which is in functions of the discharge, and this comes is established with more detail with a W by D ratios, and the ML is a function of Q and the M value, and Sheetal 1970 also established more detail between these non-dimensional forms, okay, which is considering the 42 river data. So, what am I want to look at that when you look at this regime relationships, which is extracted from the river, which is way back, still it hold good it, and there is a some spatial frequency, it is there in a meandering plant forms, which is the 6 and 18s, which is easy to remember it. Okay. If a width of the river is 1 kilometers, the meandering length will be the 6 kilometers, and meandering belt width will be the 18 kilometers. So, that's try to understand it. Okay. And also we talk about the width and discharge in the same order. Okay. If it width is 1000 meters, so we will have the discharge about the 10,000 dominant discharge. So, you can try to understand it how things are happens it in terms of dominant discharge, in terms of ML, MB and this. So, what I am telling that if you look at these regional relationships, what is developed way back in 100 years, it also tells a story to us. Either we have to accept it or we have to understand, considering that we can understand the rivers. And more precisely, we have a more data now, we can always look back at these regional equations, how whether they are valid or not valid. Because if you look at these equations, they are different, but what order of their difference when you talk about the rivers with the flood plains, the insigns rivers, the rivers in the flood plain, this is the 50 stream raging at the European rule of thumb. Okay, thumb rule says that or you have a silt clay percentage which is control these characteristics, mean flow, discharge, you can have this some series and you can have this. So, we should have a better understanding is that how these empirical equations is providing us the knowledge, and those knowledge of river we can implement it when you are trying to design river training works. Now, if you look at again, it is a compiled form of river regime relationship in terms of width. Okay. Width formula is the depth formula is slope, the velocity and the bed material size. Okay. If you look at these formulas, the Lacey's formulas is comes from evolved from canal data, what we discussed in the last class. Nixon's formula is based on the UK rivers. Pitt's formulas are from USA. The statistical methods from these Indian rivers. Also, we have muddy bench formulas is from canal and river data. Okay. So, if you look at that, the canal is more geometrically and the bed material wise not variabilities there, but if you talk about the rivers, it is having lot of variabilities. So, if you look at the Lacey's equations, again I have to put it, the W will be the 4.8 times of Q of 0.5. Okay. So, it is a 0.5 square root. The same way, if I look at the Petty's formulas, which is from the USA data, we talk about only the difference between these coefficients 4.4 q to the power 0.5. So, only these multiplications factors are changing it a to the power a q b, then same way this Nixon's also this. So, if you look at this width are having the more or less the same formulas, but in case of Indian rivers we have W is 1.6 q, okay. D is a flow depth 1.5. So, in Indian river it has a different relationship as compared to this. Why? Those questions we can always look at. If you look at, if I look at the depth formulas, okay, it is very interesting now. If you look at the Nixon's and the Petty's formulas, which give is the flow depth is a functions of 0.539 q to the power 1 by 3, okay, q to the power 1 by 3, whereas Petty's formula is just a slight bit modified with a 0.635 q to the power 1 by 3rd. Okay. So, if you look at that, only these coefficients of these two things are changing it. So, we can know the flow depth if I know the discharge accurately, the dominant discharge if I know it accurately. For in case of the Indian river, as I modified the statistical part, which is give it 3.6 q to 0.8 and also a functions with width. So, in Indian rivers this, but in case of these Petty's formulas is from the USA, Nixon's formula is derived from the UK rivers, more or less the same, but when you talk about Indian rivers, we have the values are there, and you know it, we can get the flow depth using the Lacy's equations. So, it always indicates that we can have some sort of the regional equation. So, same way you can look at how the equations are there in case of slope, in terms of the velocity and this. Okay. So, let me put it, the velocities is very close to from the Fetty's equations that 0.5 q 0.2. Okay. So, that means if you know the discharge, you can know its approximate velocity can be there from the Fetty's discharge that. But before concluding that, these regional equations are good if it is derived it properly with a more reliable hydrologic data like discharge, more reliable discharge data set, the flow depth, the width, if I have a more reliable data set, and deriving of these regional equations really plays a major roles for a river engineers. Now, if you look at the next levels, if I talk about how the lateral river migrations happens it, and if you look at these behaviors of winding of the river erosions happen, excess of sedimentations near the opposite banks. Okay, if you can look at how does this happen it, okay, regularly in pant, irregular can happen, or it can have absence. Okay, types of mantis curls. Okay, it can have a narrowing the results of the sedimentations near one back, excess of erosions rate, opposite side, and you can understand these things which are very simple way. How does river meanders happens it, types of the scrollings that regular or faint or irregular, or in case of absent can also happens it. Okay, let's today we let us conclude these lectures having talking about our understanding of rivers. If I quote from Nancy's quote that Patna is one of the oldest continuously inhabited riverine cities in the world, situated on the southern bank of the river Ganga. So, what I am to talk about that, we should have a more knowledge as we are close to habitat to the Ganges rivers, is the oldest inhabited riverine cities. You can get the history of the Patna cities and try to know it, how things are evolved in a Patna cities, which is the riverine cities in the world, the oldest ones, and that is the story of the Gangas and the Patna city are as particular to Bihar. Thank you.